Deep learning-based 6DoF robot arm control with computer vision. Abstract. This article presents the control technique for the 6 degrees of freedom, 6DoF, robot arm to pick up and drop objects based on computer vision and deep learning, DL, techniques. Control commands are performed by the human voice. Information in voice control commands is processed through the voice recognition module and converted to text. Based on the machine learning model, characteristic information from the complete text is extracted and encoded into the object recognition module, computer vision, input signal. Model DL2 is built in computer vision engineering to recognize objects on demand from voice. The outputs of the DL1, DL2, and ML networks are the information needed for converting into robot arm control signals through the DL3 network. The structure of the model DL1 and ML is not clearly mentioned in the scope of this article. A 6DoF robot model is built to perform tests to assess the feasibility of the control method. The research results have important signification for the construction of robotic control systems that use intelligent, flexible, and responsive algorithms in real time. Keywords: deep learning, computer vision, robot arm. Introduction. The robot control problem is designed for different tasks such as controlling position, trajectory, or performing tasks of picking and dropping objects. There are many position or trajectory control systems developed such as PID1, sliding mode control 2, backstepping 3, robust control 4, fuzzy logic 5, to other intelligent control algorithms such as adaptive control 6, neural network 7, machine learning, ML, 8, reinforcement learning 9, deep learning, DL, 10. However, modern robots performing pick and drop tasks need to be smarter and more flexible. In addition to identifying the single object and its position, it is also necessary to identify the object that needs to act between many different objects. Computer vision technique developed and incorporated into intelligent control systems is a viable solution to meet the practical needs mentioned above. Furthermore, robotic control techniques performed by voice are also integrated to increase the flexibility of the control system and respond to changing the task of robot in real time. The voice control system for robots based on an artificial intelligence algorithm has been reviewed in 11. An intelligent ear designed for the robot to determine the direction of the emitted sound is performed in 12. The technique of voice recognition is based on the deep learning algorithm proposed in 13. An autonomous robot is controlled by voice. Through the Google Assistant application tool on the basis of IoT technology shown in 14. The problem of object recognition using the artificial intelligence network is mentioned in 15 to 24. A neural network, NN, model is proposed in 15 to increase the object recognition efficiency on the basis of the data library VOC2007 and ILSVR 2012. A loss function adjustment structure is proposed in 16 to optimize the overlap of boundary boxes. The structure of the YOLO algorithm is described in 17, 18. The 3DoF robot arm controlled using computer vision based on NN is shown in 19. Pick-up robots using computer vision is mentioned in 20, 21. The problem of using data libraries and deep learning methods for the object recognition problem is summarized quite clearly in 22. The robotic arm control system using the combination of high-frequency brain waves and computer vision techniques is described in 23, 24, 25. This article focuses on building the control system of the 6DoF robot arm performing object pickup task based on computer vision technique using Deep Learning Model 1. Deep Learning Model 2 is used to solve the inverse kinematics problem, with the input being the position of the identified object in the workspace and the output being the value of the corresponding joint variables. The joint variable values are converted to control signals for the drive motors, ensuring the robot performs motion and object pickup. DL1, DL2 models are built and tested in Python language with support libraries. The 6DoF robot model is practically fabricated to experiment with object recognition and grasp problems. The paper consists of 3 parts. Part 1 is the introduction. The material and research method are the contents of part 2. The last part is the results of the simulation and experiment. Material and method. Control robot arm by voice recognition and computer vision. Commands by voice, in Vietnamese, via microphone will be processed and recognized through the DL1 model. DL1 output information is a complete text, including the direction of motion and object features that become the input of the ML model. Object information from the ML output is the target for the DL2 model to identify through the camera and available learning data. The rest of the ML output combined with recognized object information, position, object type, color, shape, gathered as input to the DL3. The outputs of DL3 are the value of the joint variables that control the robot to perform the task as required. The overall model of the control system can be illustrated in Fig 1. Voice recognition by model DL1. Resolution, sharp enough to distinguish objects. The frame of camera rate should be fast enough to ensure the module's real. The robotic arm receives voice commands from the operator using the voice recognition module that converts from human voice containing control information to text in the program. The robot control information contained in the voice includes information such as the direction of the movement of the robot, turn to the left or the right, what action the robot needs to perform, the action of grabbing or dropping, identifying the object, wheels, trays, boxes, distinguishing features of objects, color, shape, size, The input voice and the output control signal must be defined to solve the robot control target. In essence, the voice recognition module is a natural language processing problem, a DL1 model built in order for the network to learn how to convert information from voice to text. The steps to perform the voice control system are determined as follows. Information. Object recognition based on computer vision technique with DL2 model. After the system recognizes the voice command, the robot arm begins to move in the workspace. At the same time, the camera performs the continuous imaging task to detect and recognize the required object according to the output information of the ML model. When an object is recognized, information about the position of the object is converted to a control signal that moves the gripper to the position of the object to perform a programmed action. The input to the computer vision module is image data taken from the camera. Image quality must be of sufficient time object detection. The output of the computer vision module is an object with information that answers questions such as, is there an object in the sight? What kind of object? What color is it? What is the position of the object? Is the object lower or higher than the frame range? Is the subject going left or right of the frame range? A DL2 network model is built to learn and recognize surrounding objects in real time to solve this problem. DL2 model is built on the basis of YOLO method 17, 18, 26, 27. Image data after being taken with the camera will be resized, divided into small cells, Fig 2. The picture is divided into NaN squares, n equals 1, 2, 3a. At each of these squares, 2 boundary boxes must be predicted, Fig 3, each boundary box contains information such as whether the square contains the object or not. Predict what type of object name, class, belongs to, predict the center of the object and the center of the box surrounding the object. Each square is a vector including m values 26. 1. Where n box is the predicted number of boundary boxes for links accordingly. The joint variable I is denoted by chi. Each square, n class. Homogeneous transformation matrices high, I equals 1a. 6. On the more specifically for model DL2, input data is the images from gallery, to network training, and camera images, for identification. The output is a tensor containing prediction information for the NaN squares. The network structure. Links are determined 29. The position and direction of the end effector link relative to the fixed coordinate system are represented by homogeneous transformation matrix D6. This matrix is calculated as follows. Consists of convolutional layers, size 3AA3, combined with max pulling, size 2AA2. The last layer is the CONV layer, with a filter size of 1AA1. The activation function for the last class is a linear function. To determine the training error, the DL3 model uses the squared error function between the training results and the predicted results, the real results of the model. According to the output structure of each box boundary, the error consists of 3 parts: confidence loss, classification loss, and localization loss. An intersection over union, IOU, function is used to evaluate the predicted accuracy of the boundary box based on the labeled boundary box parameters, sample data, 28. The larger the IOU, the better the evaluated model, good trained. The computed data for the DL3 network model is spatial coordinate set and the corresponding set of rotation angle parameters that were collected and fed into the training DL network repeatedly until the model could give control signals for the robot accurately, to meet the requirements of the motors are Servo MG995, Arduino Nano Circuit, Logitech B525720P camera, Dell Precision M680 laptop, Razer Seiren Mini microphone. The actual experimental system is shown in Fig 8. Object recognition results. The voice's command to perform motion control of the robot, in Vietnamese, is Ki Baan Phi, Li Baan Hxe Ma U Vang. This sentence has 8 syllables, each word corresponds to 1 syllable. This command in English is, turn right, grab the yellow wheel, a total of 7 syllables. After recognizing the voice, the robot starts to move in the requested direction. The next action of the robot arm depends on the analysis results of the object recognition module, yellow wheel. To conduct the yellow wheel identification experiment in 3 objects including a yellow wheel, a green tray, and a red box. The image is divided into 7 AA7 cells. The identification algorithm uses 2 boundary boxes, n box equals 2, predictions for each cell. The number of objects to be classified is 3. Class equals 3. The number of each object image in the library for training the DL2 model is 140 pieces. Each square is a vector with 13 parameters. The input is the resized image, 448, 3 RGB image. Experiencing the structure of the model with 6 max pulling layers with the size 2AA. 2. The size of the image decreased by 64 times. Input image size is 448 AA 448, output image size is 7 AA 7. The last layer has 13 nodes, so the output of the training was performed for 8.27 hours on GeForce. Network will be 7 AA 7 AA 13, predicting the required photo information. The structure of YOLO is described in TAB2. YOLO programming code in Python is shown in Fig 9. RTX 3080 GPU. The limit for training times is 3000. The results of the training after 84 epochs are shown in Fig 10 and Fig 11. The model distinguished the object with an accuracy of 92%. Control result. Network parameter DL3 controlling the robot is shown in Fig 13 with 5 outputs corresponding to 5 rotation angles of the robot joints. The network consists of 9 hidden layers with the ReLU activation function. The number of nodes per layer is presented in Fig 14. Check on test data with input as the position vector of the end effector point in the workspaces corresponds to the joint variable value. The Q value obtained. The joint variable values to control the robot arm to the position with the object, yellow wheel, are shown in Fig 15. Some positions of the robot arm during command execution are shown in Fig 16. Initial position. Rotate and stop at object recognition position. Pick up the object. Move the object to the required position. Conclusion. The 6DOF robotic arm control system has been built and tested by an experimental model based on computer vision and voice recognition techniques. Accordingly, the voice from the model is Q recognition module through building the DL1 network model with a data library in Vietnamese has been completed. DL2. The accuracy is 98.67% on the test data set. Network model is built to recognize objects through data from the available photo library and images transferred from the camera. The calculation of control signals transmitted to the robot's drive motors is performed by the DL3 model based on information about the motion direction and position of the recognized object in the workspace. The robotic arm control system based on computer vision is completely independent of the internet connection. The results of experiments on the actual model show the correctness and reliability of computer vision techniques with a recognition accuracy of 92%. However, this study has not considered the evaluation of the robot arm's motion accuracy due to fabrication errors, the processing rate of the control system in real time. The research results have an important meaning in the research and development of advanced intelligent algorithms combining speech recognition, computer vision, and the integration of IoT systems.